Welcome to another video on function transformations. This video deals specifically with a reflection about the x-axis and the y-axis. So if we're comparing f of x to the function in this form, we'll be taking a look at how the sine of a and the sine of b affect the graph of the original function. So even though we have talked about vertical and horizontal stretches and compressions, we haven't talked about what happens when we change the sign of a and b. Y equals negative f of x reflects f of x about the x-axis. Remember, f of x is equal to y. So if we change the sign of the y coordinates, that would reflect the graph about the x-axis. If y equals f of negative x, this would reflect f of x about the y-axis. And here, we're changing the sign of the x coordinates, and therefore would reflect the graph across the y-axis. Let's go ahead and take a look at this using t-tables for comparison. If f of x equals the square root of x, then to determine y we would take the square root of these x values. So the square root of 0 would be 0, square root of 1 is 1, square root of 4 would be 2, square root of 9 would be 3. Now let's compare this to g of x, which equals negative f of x, which equals negative square root x. So the square root of x would still be the same each time, but now we would take the opposite of that. So we would have 0, negative 1, negative 2, and negative 3. And notice that if you change the sign of the y coordinates, this would reflect the graph across the x-axis. Now if we let h of x equals f of negative x, this would equal the square root of negative x. Remember, this radicand must be greater than or equal to 0 to take the square root of it. So if we change the sign of the x coordinates, so if we change the sign of our input x, it would make our radicand either positive or 0. So we'd have 0, 1, 2, and 3. So since we changed the sign of the x coordinates, it would reflect it across the y-axis. If we were to graph these three functions on the same coordinate plane, we would have our original function in blue. If we change the sign of the x coordinates, or reflect this graph about the y-axis, we would have h of x, which equals f of negative x. We change the sign of the x coordinate. And in green, if we reflect it across the x-axis or change the sign of the y coordinates, we would have g of x, which equals negative f of x. Let's take a look at an animation of this. So what we see here is the original function in red, and we'll see the transformed function in blue. We'll start by changing the value of a from positive 1 to negative 1. Here you are seeing a vertical compression, and then as soon as a turns negative, we'll see a reflection across the x-axis, and as soon as a equals negative 1, the transformed function in blue is a perfect reflection of the original function in red across the x-axis. Let's now take a look at what happens when b changes from 1 to negative 1. So right now b is equal to positive 1, and as we decrease b, you'll see a horizontal stretch, and then when b turns negative, we'll see a reflection across the y-axis. And when b equals negative 1, we have a perfect reflection of the red function across the y-axis. Let's go and take a look at some of our own examples now. Again, the first thing we want to be able to recognize is that our parent function would be g of x equals the absolute value of x, which we should know by now is just a v that opens upward. And some of the key points on this graph would be 0, 0, 3, 3, and then maybe negative 3, 3. So f of x is really just the opposite of g of x, which is equal to negative absolute value of x. And here we should be able to recognize that a is equal to negative 1, or that we're changing the sign of the y coordinates. Therefore, it's a reflection across the x-axis. So instead of opening up, the given function will open down. So we can just change the sign of these y coordinates. So we'd have the point -3, -3, still the origin, and then 3, -3. This would be the graph of f of x equals negative absolute value of x. Again, the original is in red, and the transformed or reflected graph is in blue. And here we have f of x equals the cube root of negative x. So our parent function would be the cube root of x. Now this one may not be quite as obvious as some of the others that we've done. Let's go ahead and sketch this parent graph. So if we take the cube root of -8, that would be -2. So we'll plot the point -8, -2, 0, 0. And then the cube root of 8 would be 2. Let's find two more points. The cube root of -27 would be -3, somewhere here. And the cube root of +27 is 3. So the parent function looks something like this. But we want to graph f of x equals the cube root of -x. So f of x is equal to g of -x, which is equal to the cube root of -x. So here notice we're changing the sign of the input or every x coordinate. So let's go ahead and just replot these points by changing the x coordinates. So we still have 0, 0. And then instead of 8, 2, we'll have -8, 2. Instead of 27, 3, we'll have -27, 3. And instead of -8, -2, we'll have +8, -2. And lastly, instead of -27, -3, we'll have +27, -3. So our transformed graph is green and would look something like this. And now we can see it's a reflection about the y-axis. Okay, in the next two videos, what we're going to do is take a look at various transformations all combined at the same time to finish off the topic of function transformations. Thank you for watching.